In this video, we're going to work with properties of power series. We're going to combine and create new power series using addition, subtraction, and multiplication. We're going to integrate and differentiate our power series term by term. The reason we're going to want to do all of that is because it allows us to represent functions in terms of their elementary functions that we know the power series for. So if we can take a function, write it as an elementary function that we know the power series for, we can take a more difficult combined function and do the combination of the power series that represents the elementary ones to be able to represent this function. And it also allows us to define new functions that cannot be written in terms of elementary functions. And this is really helpful when we're solving differential equations for which there is no solution in terms of elementary functions. So the first one we're going to do is combining functions. So let me erase this line I put on there because we don't need that. And suppose you have two power series. You have c sub n, x to n. And I just want to say that we're starting at n equals 0 to infinity. And we have d sub n, x sub n. And both of those power series converge to some functions f and g respectively on some interval that they share I. Then I can add these two power series, and if they converge, if they both f and g, the functions converge on this common interval I, then the addition or subtraction will also converge on this interval of I. And then the next two here is for any integer m greater than 0 and for any real number b, the power series n equals 0 to infinity of this real number b multiplied by x to the m, c sub n, x to the n will converge to that real number b times x raised to the m times that function f of x on I. And then for any integer m greater than or equal to 0, then any real number b, the series n equals 0 to infinity of c sub m multiplied by this real number b, x raised to the m, and that whole thing raised to the n, will converge to the function f of that number b multiplied by x to the m for all x in such that bx raised to the m is in this interval I. Cool. All right, now let's go through this problem. Find the interval of convergence for each of the series and then find the interval of convergence for s of x, c of x, and b of x, where b of x is equal to this series, s of x is equal to this series, and c of x is equal to this series. Now, you're going to do the interval of convergence, find your radius of convergence first, however you feel appropriate, whether it is the ratio test or the root test. But I'm going to give you the interval of convergence for each one of them, and then we're going to talk about the addition and subtraction of these. Should I add and subtract these? So for b, my interval of convergence is negative e squared over 4, comma e squared over 4. And I check the endpoints. The interval for convergence for c is going to be negative 10 e squared and then positive 10 e squared, and again checking the endpoints. And then for s, I got negative e squared and then e squared. So if I were to add s of x and c of x, I've got to have the interval of convergence that is satisfied for both of these two parts. Now you can see that this is smaller than this because they both have e squared. But 10 times e squared is a larger number than just e squared. And so the interval of convergence for these two will be where they are both defined, and they are both defined between negative e squared and e squared. Now, if I wanted to find the interval of convergence, say, between s of x, and I wanted to add to it b of x, and I wanted this interval of convergence, in this case, this is the smaller set that's contained within this larger set, so its interval of convergence would be negative e squared over 4, and then e squared over 4. So now we've got one that is slightly different than what we've seen before. we want to find the radius of convergence for 5 over x squared minus x minus 6. I'm going to use that definition that we've used before, which is 1 over 1 minus y is equal to the series as n equals 0 to infinity of y to the n. So I'm going to use partial fraction decomposition to rewrite this. So I'm going to rewrite this as f of x is equal to 1 over x minus 3 minus 1 over x plus 2. Now, unlike the one that we had in class where we talked about the center being at 3, I don't know if the center is anywhere else other than 0, so I'm going to make the assumption it's at 0, which means I need to rewrite these to match this form. So I'm going to rewrite this as dividing everything by negative 3, so negative 1/3, and then this becomes negative x divided by 3. This becomes plus 1. And here I'm going to divide everything by 2, so I have 1/2 over x divided by 2 plus 1. Then I'm going to rewrite this as negative 1/3 over 1 minus x thirds, and then minus the 1/2 over, rewrite this as x minus a negative x over 2. Now, using this, I'm going to rewrite this as negative 1/3, the summation of n equals 0 to infinity of x over 3 raised to the n minus 1/2, the summation of n equals 0 to infinity of negative x over 2 raised to the n. Then I'm going to go ahead and distribute the n on the x and the 3 and the x and the negative 2 and the negative 1 in the second grouping. And so I'm going to get negative 1/3, the summation of n equals 0 to infinity, x to the n, 3 to the n, minus 1/2, the summation of n equals 0 to infinity of negative 1 to the n, x to the n over 2 to the n. Now I'm going to bring in this negative 1/3 and this negative 1/2. So I'm going to have the summation of n equals 0 to infinity of negative 1/3 multiplied by x to the n, 3 to the n, plus the summation of n equals 0 to infinity of negative 1 to the n, 1 over 2, well, negative 1 over 2, x to the n over 2 to the n. And so then I'm going to get the summation of n equals 0 to infinity of negative x to the n over 3 to the n plus 1, plus the summation of n equals 0 to infinity of negative 1 to the n plus 1, x to the n, over 3 to the n, or excuse me, 2 to the n plus 1, 2 to the n plus 1. And now I'm going to combine these to the summation of n equals 0 to infinity of negative x to the n over 3 to the n plus 1, plus negative 1 to the n plus 1, x to the n, over 2 to the n plus 1. Now you can see that x to the n can be canceled out, so I'm going to have the summation of n equals 0 to infinity of negative 1 over 3 to the n plus 1 plus negative 1 to the n plus 1, x, or over 2 to the n plus 1. And then this whole thing can be multiplied by x to the n. And I could pull out a negative 1, but I think I'm going to just leave it right there. It's also asking me to find my radius of convergence. So what I would do is I would come back here and find the radius of convergence for, actually I'll go here, for this series, and then I'd find the radius of convergence for this series. Now, what I did when I found the radius of convergence, I'm just going to erase that. The radius of convergence for this first one, which is summation of n equals 0 to infinity of negative 1/3, I found my radius of convergence to be 3. I found this to be the radius of convergence of 2. And as before, we always pick the smaller of the two numbers, and so this should go right there. This has a radius of convergence of 2. And if I wanted to know the interval of convergence, I would then have to check endpoints. Okay, let's take a look at this, where we're asked to write each power series as a rational function. The first thing you should notice is that the lower limit is not 0, it's 1, so we're going to have to make this adjustment. And so since I want to put in 0 and get the same thing, so this is if I start to write it as a series, the terms. My first term would be 1 over x to the 1, and then my second one would be 1 over x to the 2, and etc. But I want to start this so n equals 0 to infinity, which means that I need to start this as 1 over x raised to the n plus 1. And that way, when I put in 0, I will get my first term, which is x to the 1. So there's that. Now, this is then the same thing as the summation of n equals 0 to infinity of 1 over x to the n multiplied by x to the 1, which is the same thing as n equals 0 to infinity of 1 over x to the n times 1 over x. Now, since this x is not attached to the x to the n now, I'm going to bring that out front. So this is 1 over x, the summation of n equals 0 to infinity of 1 over x to the n. Now I can use the definition for this part. I may need to write this as x raised to the negative 1 raised to the n, if that helps. So then this becomes the 1 over x, that comes from right here, and then multiplied by 1 over 1 minus x raised to the negative 1. And then I can just multiply that 1 over x through, just multiply the x in the denominator. I'm going to get 1 over, I'm going to get x minus 1. And that is my final answer. All right, let's take a look at our second example here. I notice that this again starts at 1, and I need it to start at 0. So what I'm going to do is find the first couple of terms and then see what I need to do to adjust this so that it starts at 0. I'm going to put in 1, and so I'm going to get 1 over x minus 3, 2 multiplied by 1 minus 1. My next term would be 1 over x minus 3, 2 multiplied by 2 minus 1, and then it would continue. So this first term is 1 over x minus 3, and I get to the 1 power, and the next term would be 1 over x minus 3 raised to the 3 power, and I'm guessing that the next one would be 1 over x minus 3 raised to the 5th power. Let's just check that really fast. This third term would be 1 over x minus 3, 2 times 3 minus 1. Yeah, so that check. Now if I pay attention to my powers like a sequence, I have 1, 3, 5. When I put in 0, I should get 1. When I put in 1, I get 3. And when I put in 3, I get 5. Or put in 2, I get 5. So I know that my d is 2. So this is what I think I have. I have the summation of n equals 1, or n equals 0 to infinity, of 1 over x minus 3 raised to the 1 plus 2n. Now let's check it. I put in 0. For here, I'm going to get 1. I put in 1. I'm going to get 3. I put in, so that one checks and that one checks. I put in 2. I'm going to get 5, so that one checks. So this is where I am. Now, I'm going to do the same thing as I did before, is I'm going to rewrite this as the summation of n equals 0 to infinity of 1 over x minus 3 raised to the 1, and then x minus 3 raised to the 2 raised to the n. So then this becomes the summation of n equals 0 to infinity. Well, actually, I'm going to go ahead and bring out front of the series the 1 over x minus 3, because that is no longer attached to the n part. and then the summation of n equals 0 to infinity of, and then I'm going to rewrite this as x minus 3 raised to the negative 2 raised to the n. I'm going to use that definition of 1 over 1 minus y is equal to the summation of n equals 0 to infinity of y to the n, and I'm going to go backwards with that. So I have 1 over x minus 3 to begin with, and then I'm going to have multiplied by 1 over 1 minus x minus 3 raised to the negative 2. So this is 1 over x minus 3 multiplied by 1 over 1 minus 1 over x minus 3, the quantity squared. Distributing this through, I'm going to get 1 over x minus 3 minus 1 over x minus 3. And I have a complex or nested fraction, so I'm going to multiply by my magic 1, and my magic 1 happens to be x minus 3 in the numerator and x minus 3 in the denominator. And I'm going to get x minus 3 in the numerator. I'm going to get x minus 3, the quantity squared, minus 1. And if you are inclined, you can multiply out the denominator. And you're going to get x minus 3. And then in the denominator, you're going to get x squared minus 6x minus 9, or plus 9 minus 1, so plus 8. And there is your rational function that can be represented by this series. All right, this looks like a whole bunch of fun. Again, pay attention to where you start. So I have n equals 1. I need this to start at n equals 0. So I'm just going to look at each one individually. Well, actually, I'm going to do this. I'm going to go ahead and write this as n equals 1 to infinity of 1 over x minus 3 raised to the 2n minus 1. And then minus the summation of n equals 0 to infinity. Well, that's actually, excuse me, n equals 1 to infinity, not 0, because I have to make that adjustment, of 1 over x minus 2 raised to the 2n minus 1. Now, we just did one in which we see that we started out with 2x minus 1, and to make that adjustment to move it over, we ended up having to have 2x plus 1. So we know, since we just did one that's similar, this is going to be n equals 0 to infinity of 1 over x minus 3 raised to the 2n plus 1 minus the summation of n equals 0 to infinity of 1 over x minus 2 raised to the 2n plus 1. And then, as before, we're going to have 1 over x minus 3 will come out, the summation of n equals 0 to infinity of 1 over, well, actually, again, I'm going to write it like we just did it. I'm going to write this as x minus 3 raised to the negative 2 raised to the n minus 1 over x minus 2, the summation of n equals 0 to infinity, of x minus 2 raised to the negative 2 raised to the n. So I get 1 x minus 3, 1 over x minus 3 times 1 over 1 minus 1 over x minus 3 squared minus 1 over x minus 2 times 1 over 1 minus 1 over x minus 2, the quantity squared. This then becomes 1 over x minus 3 minus 1 over x minus 3 minus 1 over x minus 2 minus 1 over x minus 2. Multiplying by my magic 1, which is either x minus 3 over x minus 3 or x minus 2 over x minus 2. I'm going to have x minus 3 over x minus 3, the quantity squared, minus 1 over x minus 2, the quantity squared, minus 1. Whew. Not a rational function yet. We'd like it to be a rational function. It's not quite there yet. And so it'd have a same common denominator. I can do a couple of things. This one is going to be x squared if I were to multiply it out. X squared minus 6x plus 8. And this would be x squared minus 4x plus 3. This one is going to factor into x minus 2, or x minus 3, x minus 1. And this one's going to factor into x minus 2x minus 4. So having a common denominator, I'm going to have x minus 3. This is going to need to be multiplied by x minus 3, x minus 1, minus the second grouping will be need to multiply by x minus 2, x minus 4, and then it's all over x minus 2, x minus 4, x minus 3, and x minus 1. And then if that cleans up, it cleans up. And that would be lovely if it did, but I doubt it will. So that is my rational function, is represented by this loveliness. All right, so calculate the present value P of annuity in which $10,000 is to be paid out annually for a period of 20 years, assuming the interest rates of R equals 0.03, R equals 0.05, and R equals 0.7. So in other words, 3%, 5%, and 7%. Those are the ones they want me to check. We have a formula for this in the textbook. The P, the present value, is a summation of k equals 1 to n of our C, which is the amount we want to get distributed every year, and then 1 plus r, that's our interest rate, as a decimal, and then raised to the k. So n equals the number of years we want this to pay out. C is the amount each year, or each payment, I should say. R is the rate. So all of these are going to be the same, with the exception of R. So it'll be the summation of k equals 1 to 20 of 10,000. Is that 10,000? No, I think I got one too many zeros. No? Yeah. Gosh darn it. 10,000, 1 plus either 0.03 raised to the k, or this would be 1 plus 0.05, or 1 plus 0.07. So they're all pretty much the same thing. Now, if I were to start writing this first one out, well, actually, let me just clean this up. K equals 1 to 20 of 10,000 over 1.03 raised to the k. Now, we know from our series that we can pull out that 10,000 out front, and it's not going to change anything in terms of my series. And then it's going to be 1 over 1.03 to the k. Now I have two choices. I can start writing this stuff out, term by term, and multiply by 10,000. Or I can get my formula sheet out, and I have a formula for the partial sum of a geometric series, which is what this is. And so the sum, a partial sum, so sum of 20, which is going to be equal to my A, which is 1 minus my R, which is 1 over 1.03. This needs to be raised to the 20 over 1 minus 1 over 1.03. Now don't forget, this does need to be multiplied by that 10,000. And so for my first answer, I get my calculator out and I get 148,767. I'm going to do it again, but now I'm not going to worry about the 1. I'm just going to do 1 minus 1 over 1.05 raised to the 20 over 1 minus 1 over 1.05, whatever that equals. Oh, don't forget. I wanted to forget, but don't forget. I'm multiplying this by that 10,000. And then my last one, the only thing that's going to change S of 20 here is I'm going to have 1 minus 1 over 1.07 raised to the 20 over 1 minus 1 over 1.07. Multiply this thing by that 10,000 again, and then whatever that equals. Now we're going to take this polynomial. We're going to write it as a power series, And then we're going to write it as a rational function. So here we go. First thing I notice is that this is not a true alternating series because alternating should be positive, negative, positive, negative, positive, negative. Okay, so that's not helpful because it's not a true alternating series. And so I start with what happens if I do x minus x to the third. So the next one should be positive. If I'm going up, this is 1, 3. The next one would be x to the fifth. And then the next one would be x to the 7th. So that works out. It looks like it's alternating now. Powers are slightly different, but that's alternating. And then I could do x squared minus x to the 4th minus, that'd be plus, the next one would be x to the 6th, and then minus x to the 8th. That might work. I can break it up into two of them. If I did that, then I would have this as the power series, the summation of n equals 0 to infinity. I have -1. I need the first term to be positive, so I just have -1 to the n. That would work. And I would have x to the, well, I think this is going to be like it did before, 2n plus 1. Let's see if that works. 2n plus 1. If I use 2n plus 1 and I put in 0, I get x to the 1, and it's a positive. I put in 2 or 1, this is a negative, and this would be 3, so that works out. Now for my second grouping, I'm going to have n equals 0 to infinity. -1 to the 0, so that's okay, that works. Or excuse me, not 0, n, that's going to work as well. And then I need x raised to the, let's say 2n plus 2. Is that going to work? So I put in 0, I get 2. I put in 1, I get 4. I put in 3, or I put in 0. So for n for 0, I'm going to get x to the 2. If I put in 1, I'm going to get 2 plus 2, which is 4. If I put in 2, I'm going to get 2 times 2, which is 4 plus 2, which is 6. So that works out. So then this, I can bring this together as a summation of n equals 0 to infinity of -1 to the n, x to the 2n plus 1, plus -1 to the n, x to the 2n plus 2. So then this is going to be the summation of n equals 0 to infinity. I can factor out -1 to the n because it's common here and here. I can write this as x raised to the 2n times x. I can write this as x to the 2n times x squared. So I can factor out x to the 2n, leaving me x plus x squared. So I've wrote it as a series. Now I need to write it as a rational function. The x plus x squared is not dependent on the summation of n equals 0 to infinity. I'm going to, since I'm reversing that 1 over 1 minus y is equal to the summation of n equals 0 to infinity. Infinity of y to the n, since I'm going in this direction. I'm going to combine these two as -x raised to the 2 raised to the n. So then this then would become x plus x squared over 1 minus a minus x squared, which would give me x plus x squared over 1 plus x squared. And there it is. There's my rational function that I wrote this thing as, I took a polynomial and wrote it as a rational function, which is kind of cool in this section. Or not, it just all depends on how you look at it. Let's take a look at B now. With B, there is not a distinct pattern like the previous one, where I could take the negative x to the third, plus x to the fifth, minus x to the seventh. I don't have that kind of distinct pattern here. So let's just start by writing all the positive first. X over 2 plus x squared over 4 plus x4 over 16 plus x5 over 32 plus dot dot dot, and then I have minus x to the third over 8 minus x to the sixth over 64. Now based on the pattern, I got positive, positive, negative, positive, positive, negative. So the next ones I have positive, positive, and then my next negative would have been negative x to the ninth. And then probably I would guess if this is 8 to the 1 and this is 8 squared, this is probably 8 to the third. So I think that's okay. So this part, I'm going to have negative out front, n equals 0 to infinity. I need in the denominator, I need 8 to the n plus 1. Yep, that would work. Because 8 to the 0, or this is 8 to the 1, would be the first one. And then 1 plus 1 is 2 is 8 to the squared, which is so 64. And then 8 to the third, that would be that one. And then for my x part, I'm going up 3, 6, 9. So I put in 0, I need 3 out. I put in 1, I get 6 out. So what I'm looking at is a 3, 6, 9. I put in 0, I need to get 3 out. I put in 6, I put in 1, I need 6 out. I put in 2, I'd better get 9 out. So I think this might be 2n plus 3. Would that work? So 2n plus 3. So I put in 0, I get 3. I put in 1, I get, nope, that isn't going to work. So what about 3n plus 3? So I put in 0, I get 3. I put in 1, I get 6. I put in 2, I get 6 plus 3, which is 9. So I think that's the power on that one. So that takes care of this grouping. Let's rearrange this so that we have x over 2 plus x over 4, or x to the fourth over 16 plus dot dot dot. My guess, well actually my next term that would go in this grouping would be x to the, since it looks like I'm moving up by 3, x to the 7th over, this is 2 to the 1, this is 2 to the 4. So this next one should be 2 to the 7th. And then plus dot dot dot. I'm going to do x squared over 4 plus x to the 5 over 32. Since this is going up by 3, this would be x to the 8 over. This is 2 to the 2, this is 2 to the 5. That means this must be 2 to the 5th. Okay, so this then is going to be the summation of n equals 0 to infinity. I need, when I put in 0, I get 1. When I put in 1, I get 4. So I think this might be 3n plus 1 over 2, 3n plus 1. Let's just do a quick check. I put in 0, I get 1 and 1. I put in 1, I get 4 and 2 to the 4th. I put in 2, I'm going to get 6, 7. Yeah, so that works out. Now, this grouping is going to be plus the summation of n equals 0 to infinity. X to the, well, I need to have 2, so let's do 3n plus 2 over 2, 3n plus 2. Now let's check to see if that works. If I put in 0, I'm going to get x to the 2 over 2 squared. I put in 1, I'm going to get 3 plus 2, which is 5, and 2 to the 5th. I put in 2, I'm going to get 6 plus 2 is 8. Yeah, so that works. And then plus, I had this, or minus, I had this last one, n equals 0 to infinity, of x to the 3n plus 3 over 8 to the n plus 1. But let's write this instead of 8, because 8 is a factor of 2, since 8 really is 2 to the 3rd. Let's write this 8 to the n plus 1 as 2 to the 3rd raised to the n plus 1. So let's write this as 2 to the 3n plus 3. So let's rewrite this denominator. So we all have 2's to the 3n plus 3. Now let's bring this all together, the summation of n equals 0 to infinity. You can see that each one of these has x to the 3n. You can see each one of these has 2 to the 3n. So I know that I'm going to have x to the 3n, that's going to factor out. I know I'm going to have 2 to the 3n, that's going to factor out. What's going to be left over in the first term is x over 2. And the second term, I'm going to have x squared over 2 squared. And then my last term, I'm going to have x to the 3rd over 2 to the 3rd. So there's my series. I realize that all of these are not dependent on n, so I can factor all of that out. So I'm going to have x over 2 plus x squared over 2 squared minus x to the 3rd over 2 to the 3rd. And since I'm going to be using 1 over 1 minus y is equal to the summation of n equals 0 to infinity of y to the n, I'm going to go ahead and combine these back in. So I'm going to write this as n equals 0 to infinity of x over 2 raised to the 3rd raised to the n. So then this is going to be equal to x over 2 plus x squared over 4 minus x to the 3rd over 8 multiplied by 1 over 1 minus x over 2 raised to the 3rd power. All right, so cleaning up this grouping into a single fraction, I am going to get 4x plus 2x squared minus x to the 3rd all over 8 over 1 minus x to the 3rd over 8. So my final rational function is going to be 4x plus 2x squared minus x to the 3rd over 8 minus x to the 3rd. And there it is. This rational function represents this polynomial. Yay! Okay, now let's multiply some power series. Suppose you have a power series, these two power series starting at n equals 0, c sub n x to the n, d sub n x to the n. They both converge respectively on the common interval I. And e sub n is going to be c naught dn, c1 d to the n minus 1. And you're thinking, what is going on? And that's because when you multiply, just very, very generically, let's multiply two binomials. Let's do x minus 1 and x plus 2. So you're going to have these two multiplied together, so you're going to get x multiplied by x. You're going to multiply these two together, so you're going to get 2x. You're going to multiply these together, you get negative x, and then you multiply these two together, and you're going to get negative 2. So c naught is the coefficient on that first polynomial, the first series, the coefficient on the highest power. D sub n would be the constant. Then you're going to have a c sub 1 multiplied, so the second coefficient on this power series is going to multiply by the second to last coefficient, and that's what's happening here. So it makes it kind of clear of what's happening with the multiplications. So then this e sub n, if that's what ends up happening, this e sub n is going to be equal to k equals 0 to n of c sub k multiplied by d sub n minus k. So then that's just taking care of the coefficients. So then if we are multiplying these two power series, the c sub n and the d sub n multiplied together is going to be this e sub n, which is this lovely thing, and then x to the n. This multiplication converges on this interval I in which f and g both share. This is known as the Cauchy product. So I'm probably saying that wrong. The Cauchy product of the series of these two. So find the power series of f of x and g of x given f and g as defined. So I'm going to write f of x as 2 the summation of n equals 0 to infinity of following the same pattern of c sub n and d sub n. So I'll write this as c sub n, x to the n, and then I'm going to rewrite g of x is equal to the summation of n equals 0 to infinity of b sub n, and then x to the n. Now, b sub n happens to be n here, so this is b sub n, and then c sub n actually is 1, so b sub n equals n, and then c sub 1 equals 1. Now the reason I'm doing that is because when I do this multiplication, I'm going to have 2 the summation of n equals 0 to infinity of x sub n, or excuse me, c sub n, b sub n. Nope. C sub n x to the n multiplied by the summation of n equals 0 to infinity of b sub n x to the n. Now, based on what we have up above here, this is going to be 2 the summation of n equals 0 to infinity of, now I'm actually going to be going to here, the summation of k equals 0 to infinity of a sub k b sub k minus, no, that'll be n minus k, right? Is that what is up there? N minus k, yep. And then I'm going to have x raised to the k. Now, focusing in on this piece alone, this summation of k equals 0 to n, excuse me, that should be to n, not infinity. Let me erase that. Let me make that to n. To n of a sub k, b sub n minus k. This is going to be the summation of k equals 0 to n of just k minus j, because that's how it's going to work for the multiplication, which is just going to be equal to the summation of m equals 0 to n of just m, where m is going to just be k minus j. And then, so this, using the trig formula sheet, becomes the upper limit, which is n, and then n plus 1 all over 2. But this is all multiplied by 2, so then this just becomes n plus 1. All right, so going back to here, This is going to be the summation of n equals 0 to infinity of n multiplied by n plus 1 multiplied by x to the k. And that is my final answer. Let's take a look at another example. And this one is considerably easier. If I have g of x and f of x being the summation of n equals 1 to infinity of x over 2 raised to the n, and I'm multiplying it by f of x, which is another summation of n equals 1 to infinity of x to the n over 2. This is going to be equal to the summation of n equals 2 to infinity. Actually, I think I'm going to use k here, and I'll explain why in a moment. So k equals 2 of c sub k x to the k. Now, why 2? Well, if I were to multiply my first one, which is x over 2 plus x squared over 4 plus x to the 3 over 8 plus ... There's my f of x. My g of x would be x over 2 plus x squared over 4 plus ... When you multiply these two, your first term would be x squared over 4. So in other words, because my first term would have been x squared, not x1, I need to start here. My index needs to start at 2. That's why I have x to the k starting at 2. That's why the index starts at 2 here. Now, focusing on c sub k. C sub k is going to be the summation of n equals 1 to the k minus 1 over 1 over 2 to the n multiplied by 1 over 2 to the k minus n. Now, if you're wondering why I have 1 over 2 to the n multiplied by 1 over 2 to the k minus n, at some point I'm going to have to multiply the very first constant of my first series as I write it out, and it will be multiplied by my second or my last constant as I multiply it out. So this represents the coefficient on my first power series, and this represents the last coefficient on my power series. So these gives me all the combinations of my first and my last, my second and my second to last, and all of the combinations that need to happen. That's why it's 1 over 2 to the n times 1 over the k minus n. This then becomes a summation of n equals 1 to k minus 1 of 1 over 2 to the k. Now, this is a geometric series. If I use my formula for the geometric series, this is just going to become k minus 1 over 2 to the k. Because my r happens to be 2 to the k, and since 1 over 2 to the k, 1/2 to the, actually my r is 1/2, excuse me. My r is 1/2, because it would be 1/2 to the k. My r is less than 1, so I'd use the partial sum of a geometric series to get that. Okay, so then I'm going to go back here, and I'm going to have the summation of k equals 2 to infinity of k minus 1 over 2 to the k multiplied by x to the k. And that's my final answer on that one. So here it is, my final answer right here on that second one. Now, I can integrate and differentiate power series. I can do it by term. So suppose we have the power series of n equals 0 to infinity of c sub n x minus a to the n, and it converges on this interval from a minus r to a plus r for some r greater than 0. Then I can go ahead and start writing it out, and then I can differentiate it term by term. And then when I differentiate it term by term and bring it back together as a series, notice that it's just like we expect. This n comes down as a multiplier. I have x minus a to the n minus 1, and the thing that changes is I am now shifted over 1. Instead of starting at 0, I'm going to start at 1. And that's pretty much the gist of differentiation. So I don't necessarily have to write out all of the terms to realize this is what it turns out to be. I just shifted over 1, bring down that power. Can I do it a second time? Absolutely. And then for integration, so I have this integration and I have this constant when I integrate. I have n equals 0 to infinity. I have c sub n. Notice when I integrate, I have my power plus 1 and I have to divide by that power plus 1. And again, if I want to, I can go ahead and do it term by term, and I'm still going to get this answer. Now, this is telling me to differentiate term by term. So what I would do is I would write this as x to the 0 plus x to the 2 plus x to the 4 plus x to the 6, and etc. If I differentiate that, then x to the 0 is 1, so that's going to give me 0, plus 2x to the 1, plus 4x to the 3rd, plus 6x to the 5th. The next one would be 8x to the 7th. If I factor out a 2, I'm going to get x to the 1 plus 2x to the 3 plus 3x to the 5 plus 4x to the 7th, which would give me 2 the summation of n equals 0 to infinity of, let me see, n plus 1, x to the n plus 1. No, it would be 2n plus 1. Now, this is equal to 2 summation of n equals 1 to infinity of, instead of starting at 0, I'd start at n here, x raised to the 2n minus 1. Let's check that out. If I put in 1, I get 1 times 2, so my first term would be 2, and I'd have 2 times 1, which is 1 minus 1, or 2 minus 1, which is 1, so that works. I put in 2, I get 4. Yeah, okay, so that works. But this is the same thing as the summation of n equals 1 to infinity of 2n x to the 2n minus 1, which is exactly what I've got if I would have just differentiated that in the first place. So those are the summation of n equals, it was a terrible summation. I was trying to get away with not doing it again, but it didn't work out. N equals 0 to infinity of x to the 2n. Regular differentiation, I would have had 2n come down out front as a multiplier. I would have x to the 2n minus 1 because that's a regular differentiation. But I couldn't have started at 0 because if I started at 0, I would have had, here I would have had x raised to the negative 1, which is not a polynomial. That would have actually have been a 1 over x, and that wouldn't have been a polynomial. So that's why we could have just moved it over 1. So here it is asking me to do it term by term here, and then I got the same answers if I would have just differentiated and remembered to shift over 1 to ensure my very first term, all my powers, because I'm finding a power function, all of my powers have to be positive or 0. Okay, now the same thing with the integration, right? So if I were to go ahead and expand this out, because I have nothing better to do with my life, I'd write this as 2 times, I'd have negative 1 to the 0, x to the 1. My second term would be plus negative 1 to the 1, x to the 3. Yeah, because I have 2 times 1 plus 1. My next one would have been negative 1 to the 2, x to the 5, plus dot, 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 dot. And this then, if I were to write this, I would have 2, I'd have x to the 1, and then I'd have minus x to the 3rd, and then plus x to the 5th, plus dot, 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 dot. And then I would start the integration. So I have 2, the integral of x dx, minus the integral of x to the third dx plus the integral of x to the fifth dx plus dot dot dot. This would be 2. My first one would have been x squared over 2 minus x to the 4 over 4 plus x to the 6 over 6 plus dot 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 dot. I'm going to go ahead and multiply that 2 back through. So I'm going to have x squared over 1 minus x to the 4th over 2 plus x to the 6th over 3 plus dot 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 dot. This then becomes the series as n equals 0 to infinity. I have negative 1 to the n. That will give me positive and negative, that's right. Then I'm going to have x raised to the 2n plus 2. Let me just do a quick check. Put in 0, I get 2. I put in 1, I get 4. I put in 3, I get 6. Yeah, that works out. And then in the denominator, it looks like it's going to just be n plus 1. Let's check that out. I put in 0, I get 1. I put in 1, I get 2. I put in 2, I get 3. Yep, okay, that's cool. That all works out. And this is what I think it is. Now, let's go back to just integrating this thing. So I have the summation of n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1. Now I have this 2 out front as well. If I were to integrate this 2, and I'm going to write this as x to the 2n plus 1. Now we're integrating this with respect to n instead of with respect to x. I would add 1 here and then divide by that 2n plus 2, right? So I would have plus c, and I'd have some plus c. So I'd have 2, and then I'd have x to the 2n plus 2 over 2n plus 2, and then I'd have a plus c. I should say I have a plus c if I were to just integrate this. And then just ignoring the plus c, I would just have x to the 2n plus 2 over n plus 1, because in the denominator I can factor out a 2, leaving me n plus 1, and then you can see those 2 will cancel. So that's cool. However, if I have this right here, I need to be able to put in my 0, and that works. Cool. I just have to do the alternating part. And so, yeah, I could have just integrated it. And if I would have just integrated it, I would have just got as an answer the integral of n equals 0 to infinity of negative 1 to the n, x to the 2n plus 2, over n plus 1. So I could have just integrated it. I would recommend, however, you do a couple of terms just to make sure you have the alternating correct. But yeah, so that works out. And if you put in 0, you don't have to do any alterations of starting somewhere else and adjusting. So now we're asked to evaluate each infinite limit by identifying it as the value of a derivative or an integral of the geometric series. So the first thing I'm going to do, since I need an f prime right here, I need an f prime right there, is I'm going to find f prime here. So f prime of x using regular differentiation, and remember we move over 1 from n equals 1 to infinity to n equals 0. Bring that power down, x to the n minus 1, so we get that part. Now if I do f prime of 1/2, this is going to be the summation of n equals 1 to infinity of n raised to the 1/2, or n times 1/2 raised to the n minus 1. But I don't want n times 1/2 raised to the n minus 1. I want n over 2n. So I'm going to multiply this side by 1/2, which means I need to multiply this side by 1/2. And so I'm going to get 1/2 f prime of 1/2 is equal to the summation of n equals 1 to infinity of n multiplied by 1/2 raised to the n, which means this right-hand side is going to be the summation of n equals 1 to infinity of n over 2n. Now, going back up to the fact that f of x is equal to the summation of n equals 0 to infinity of x of n, and that means f of x must have been equal to 1 over 1 minus x, because remember, that whole definition of 1 over 1 minus y is equal to the summation of n equals 0 to infinity of y to the n. That whole shenanigation. If I were to do the derivative now of this, I'd get f prime of x, and this is going to be negative 1 over 1 minus x, the quantity squared, multiplied by negative 1, which means f prime of x is equal to 1 over 1 minus x, the quantity squared. F prime of 1/2 is equal to 1 over 1 minus 1/2 the quantity squared, which gives me 4. Cool. Oh, cool, because I can go back here and say this is 1/2 multiplied by 4. So then this lovely series is going to be equal to 2. So n equals 1 to infinity of n over 2n. The answer is going to be 2, which means it converges. And that's it for this video. Long video, lots of stuff.